Welcome to the deep dive. Today we're jumping into coordinate geometry.
That's right.
And specifically, we're focusing on reflections, how things look in a mirror, but
Yeah,
mathematically on a 2D plane.
exactly. It's all about location. Our source material uh, reminds its coordinate geometry, uses those two numbers, coordinates, to pin down any point.
Right, the X and Y coordinates.
Yep, you've got the horizontal x-axis, the vertical y-axis, and they cross at the origin,
0.
the dead center, pretty much.
Right.
And any point, x, y, tells you how far along horizontally, that's the x, or abscissa.
Abscissa, right.
And how far up or down vertically, that's the y, the ordinate. It gives a unique spot.
Okay, so building on that foundation, we're looking at reflections. The source uses that mirror analogy, which I think is helpful.
It is. Just like your reflection seems as far behind the mirror as you are in front.
Uh-huh.
A reflected point in geometry keeps the same distance from whatever line you're reflecting it across.
Okay, and there's specific notation for this, right?
There is. We use M for reflection, M sub L, where L tells you the line or point you're reflecting across or through.
So like M sub X for the X-axis?
Exactly. M sub X for the x-axis,
Got
my
it.
dollar for the axis, and oval for reflecting through the origin.
Got it. So our mission today basically is to get a real grip on how these reflections, 7 XMLers, actually change the coordinates of points and maybe even whole shapes.
That's the plan,
right.
understanding those transformations.
Okay, let's start with the X-axis then. The line Y was 0. What's the rule here?
The rule is 1xy.
Okay, 1xy or xy.
Okay, 1xy, xy. So what's that telling us? What's actually changing?
Well, the key thing here when you reflect across that horizontal X-axis is the X coordinate. It doesn't change. It stays exactly the same.
Please put.
But the A coordinate, the ordinate, that's what flips. If it was positive, it becomes negative. If it was negative, it becomes positive.
Ah, okay. So it just inverts the sign of the y.
Precisely.
The source gives some examples, right?
Mhm.
Like 2, 3. Yeah, take 2, 3. Reflected across the x-axis, the x, which is 2, stays 2. The y, which is 3, flips to 9, 3. So you get 2, 9 of 3.
Makes sense. And if you started with 2, 9 of 3.
Same rule. Number of 3 gives you 2 plus 3. The 9 of 3 flips back to 3.
Okay. And it works for negative X values too, like 9 of 5, 7.
Yep. Negative 5, 7 is negative 5. 9 is a 7 is negative 5 into 7. The x negative 5 is unchanged. The y 7 becomes 9 to 7.
And generally, num is B becomes neta
You
B.
got it. The x part stays. The y part b flips to b.
So if you're trying to picture this, reflecting across the X-axis is like flipping the point vertically over that line. The side-to-side position doesn't change.
That's a perfect way to think about it.
Okay, what about the Y-axis then? The vertical line, XY.
All right. So for the y-axis, the rule is Meneve xy xy.
Min X, Y, XY. That looks kind of symmetrical to the first rule, doesn't it?
It does, yeah. The rules are swapped. This time, when you reflect across the vertical y-axis, it's the coordinate that stays the same.
Okay, the up and down position holds.
Right. And the x-coordinate, the abscissa, that's the one that changes its sign.
Yeah.
Positive x becomes negative, negative x becomes positive.
So it's a horizontal flip this time.
Exactly. Let's look at the examples. Mitral of 2, 3.
Okay, Y stays 3. My stays 3X flips from 2 to negative 2. So might at 2, 3.
Perfect. And might of 2, again, is 3.
Y stays minus 3. X flips from 2 to negative 2. So minus 2, negative 3.
And by is 7. X flips from minus 5 to plus 5.
Yeah.
So 5, 7.
You're seeing the pattern, and generally mitral of B becomes AB.
Right. The y part b stays. The x part a flips to a. So reflecting across the y-axis keeps the vertical position but flips it horizontally.
Couldn't have said it better myself.
Okay, one more main one. Reflection in the origin, maticus.
Yes, matiches. The rule here is X lies, matich Y.
Matis y way. So this one changes both coordinates.
It does. Reflecting a point through the origin flicks the sign of the X coordinate and the sign of the A coordinate.
It's like doing both flips at once.
Kind of, yeah. Or think of it as swinging the point 180 degrees around the origin. Okay, I can visualize that. The examples. $2, 2 and 3, 3.
Both signs flip. So naticus 2, naticus 3.
And models of 2 negative 3.
Again, both flip. x2 becomes maticus 2. Y equals 3 becomes plus 3. So maticus 2, 3.
And negative 5, 7.
Naticus 5 flips to 5.
Stop.
7 flips to naticus 7. So 5 never 7.
And finally, dollars of A does work.
Both flip signs, giving you AB.
So reflecting through the origin sends a point to the diagonally opposite quadrant, basically.
That's generally true, unless it's on an axis. It's a point reflection, or like that 180-degree rotation we mentioned.
Interesting. Now, the source material talks about doing these one after another, like reflecting a shape twice.
Yes, compositions of transformations. You can take a shape, say a triangle ABC, reflect it using no IOC to get a new triangle ABC,
Okay.
and then you could take that triangle ABC ABC and reflect it again, maybe using known ULC to get ABC.
And you just apply the rules step by step to the coordinates.
Exactly. Find the coordinates of ABC first, then use those to find ABC.
Gotcha. This leads into something called invariant points. What's that about?
An invariant point is simply a point that, well, it doesn't move when you apply a specific transformation. It stays in the exact same spot.
It remains invariant.
Right. And the source gives us some clear cases for reflections. Think about reflecting across the x-axis, 7 to s.
Okay.
Any point that's already on the x-axis, like say 5, 0, or mega 2, 0,
Right.
its hiagret is 0.
Right.
The rule is 6y, right y becomes 6 by y,
Yeah.
which is just 850 by y. Doesn't change.
Ah, okay. So any point on the line of reflection is invariant for that reflection.
Precisely. So x0 is invariant under XOR example. 7 zeros stays to the y.
And the same logic applies to the y-axis, my.
Exactly. Any point on the y-axis has a form 0y. The rule for my is says y. So 0y becomes 0y.
Right, which is just 0y.
Yep, it's invariant. Like 0y reflected across the axis is still 0 my 3.
Okay, that makes sense. What about the origin?
The origin is special. It lies on both the x-axis and the y-axis.
So it's invariant under both XD1 and Lanor.
Correct. And it's also invariant under reflection through the origin, malada. The rule is 6 quar shwy right arrow. Applying that to 0, 0 gives a novel 0, 0, which is still 0, 0.
So the origin stays put no matter which of these three reflections you do.
That's right. And the general principle holds. Pacific line.
That's a really key idea for symmetry. Okay, quick question. Does the order matter if you do, say, an X reflection then a Y reflection?
Great question. And for Mevely-Gullers, the answer is no. The order doesn't matter.
Really?
Yeah. Let's try it. Start with XY. Apply XY. You get XY.
Okay.
Now apply Miley-Tolf to that result, XY. The rule is this XY, so it becomes like XY, which is max Y.
Okay, XY. Now, what if we did Mylar first?
Start with XY. Apply Miley-Tolf, you get an XY.
Yeah.
Now apply Miley-Tolf to that rule is 6Y, so it becomes XY, which is XY.
Hey, it's the same result. XY.
Exactly. And notice, XY is the rule for Mahler, reflection of the origin.
Whoa. So reflecting across the x-axis, then the y-axis is the same as just reflecting straight through the origin.
That's it. Sosik epskinal, followed by the medina, and my vedipose also equals metal. We say they commute.
So circa my certe Michael's mother more. That's neat.
It is. And the source mentions other related properties too, like Nalar followed by Melis actually gives you Mylar.
Oh, wow.
And Miller followed by Meller gives you Mibanas. They form a kind of interconnected system.
That hints at some deeper structure there. Okay, we've talked axes and origin, but can you reflect across other lines, like lines parallel to the axis?
Absolutely. The concept extends. You can reflect across any line. The source specifically looks at lines like XA vertical and YHA horizontal.
Where A is just some number.
Right, so X2 or Y3, for example.
Okay, the source has an example, reflecting P13 across the line melee. What happens?
Okay, picture the vertical line of O2. That's our mirror. The point P is at L13. How far is it horizontally from the line X2?
Uh-huh. From X1 to X2, that's 3 units to the left.
Exactly, 3 units to the left. So its reflection P must be 3 units to the right of the line X2.
Okay, 3 units right of X2 would be X is 2 plus 3 was 5.
Right, and the Y coordinate doesn't change because the reflection line is vertical. So P is 5, 3.
Right, 3. Got it. The Y stayed the same. The X moved to the other side of the line, same distance away.
That's the principle. Same perpendicular distance.
Let's try the other one. Reflecting Q2, 1, across the line, Y3.
Okay, now our mirror is the horizontal line Y3. The point Q is at 2, 1. How far is it vertically from Y3?
From Y1 down to Y3, that's 4 units above the line.
Perfect. 4 units above. So its reflection Q must be 4 units below the line Y3.
Below Y3. So Y negative 3, 4, and negative 7.
Exactly. And the X coordinate doesn't change because the mirror is horizontal. So Q is 2 nicus 7.
2 negative 7.
Yeah.
Okay. It really helps to visualize that distance from the mirror line. The source mentions graph paper helps.
It definitely does, especially when you're starting out. You can literally count the squares. Another way to think about it, the midpoint between the original point and its reflection always lies on the line of reflection.
Ah, that makes sense too. Okay, so reflections work for points. What about whole shapes, like triangles or squares?
You just apply the reflection rule to each corner, each vertex of the shape.
So reflect A, reflect B, reflect C for a triangle.
Exactly. You find A, B, C, and then you connect those new points. You'll get the reflected triangle.
And properties like the area of the triangle, does that change?
No, reflections are rigid transformations. They don't change size or shape, so area, lengths of sides, angles, they all stay the same. collinearity too, points on a line, stay on a line.
Okay. The source had that example of reflecting triangle ABC to ABC, then to ABC.
Right, and asking for a single transformation from ABC to ABC.
Yeah.
That tests understanding the composition, like how Mark and Mari might combine.
Or creating shapes. Reflecting points and connecting them to make a parallelogram or something.
Yeah, it shows how these basic transformations are building blocks in geometry. You can construct things using reflections.
Okay, let's try and sum this up. We've covered quite a bit about reflections in coordinate geometry.
We have. I think the key takeaways are the rules. Changes the x sign, I changes the x sign, no knows changes both signs.
Trip xy goes to 6y and lex y respectively.
Right. And then the idea of invariant points on the line of reflection don't move.
Especially the origin being invariant for all three main types.
And the commutativity thing of Lex and Euler's can be done in either order, and their combined effect is the same as Euler's.
Plus, the idea extends to lines parallel to the axis, like xa and ya, using that equal distance concept.
That's a good summary.
So, a final thought for you listening. How might these ideas, these simple rules of reflection, show up elsewhere? We think of geometry, maybe, but what about computer graphics, flipping images?
Definitely. It's fundamental there.
Or physics, optics, how light reflects, even art and design. Symmetry is often based on reflection.
It's true. The mathematical structure underlies a lot of visual phenomena.
So maybe think about how understanding these transformations, just flipping coordinates, could give you a different lens on things you see or work with. Could visualizing reflections unlock something new? It's worth pondering. And of course, there's a whole world of other transformations in coordinate geometry waiting if this sparked your interest.